Hi there. We're going to jump right into discussing enzymes and the importance of enzymatic reactions. So an enzyme is a protein. And so there are examples of non-protein enzymes, but we're just going to, because most enzymes are proteins, just going to write down that in general, enzymes are proteins that speed up chemical reactions. And they do it by lowering the amount of energy needed for that reaction to occur. So I'm just going to put it like that, okay? So enzymes are used continuously in pretty much all metabolic reactions that occur within cells. Enzymatic reactions decrease the amount of energy needed and increase the rate of a reaction. And so without enzymes, reactions would still occur, but they probably would not sustain life. And if they did sustain life, it would probably be very, very simple life forms. So enzymes are very specific. They're typically named for their substrate. Example, lactose is a carbohydrate. The enzyme that breaks lactose down is called lactase. So they're named for their molecule that they actually work on. Couldn't think of the name, sorry. Enzymes also have an active site that is very specific to whatever they work on. And so in this case, lactase might have an active site, and this would be a very weird molecule, but, and say this is lactose. This is what lactose looks like. So lactose is there, and it fits only lactase. No other molecules can fit there in general. Enzymes are used over and over again, and so you need a very small amount of enzymes to do any reaction. And so how do they decrease the amount of energy? If you look over here, when an enzyme meets with the substrate, the reaction occurs at a much more rapid pace. So this is the reaction occurring with an enzyme, and this is the reaction occurring without an enzyme. So this difference in energy here is the energy that enzymes save the cell from having to use. And when they do that, they allow that cell to work at a much more efficient or in a much more efficient mechanism or way. So when you look at this reaction here, I know I kind of drew all over this page, but hopefully you can see that the reactants have a lower energy than the products. So this is a higher energy. And so that type of a reaction, remember, is known as an endergonic reaction. And if it's an endergonic reaction, it's also called an anabolic reaction. So let's go to the next slide, and we'll talk about how enzymes and substrates actually work together. So here's an enzyme, and it has a specific shape. That shape allows a substrate to fit. So the region that the substrate sits in is called an active site. So this here is a substrate. This is the active site. The substrate binds to the active site of the enzyme, and then the enzyme is going to basically give the substrate a little hug, that's how I think of it, and either build or break bonds So stress the bonds, and they, in this case, they're causing a breakdown. So this would be a catabolic reaction. Okay. Where you have one substrate that binds, this is the reactant, and you have two products that are produced. So this binding is known as induced fit. The term induced fit means that the enzyme actually, once the substrate comes in to bind, the enzyme will actually form around the substrate, will kind of form fit around the substrate. So it's kind of a flexible lock, if you think of it that way, okay? Enzyme forms or moves to accommodate substrate. Okay, so that's that induced fit. So we used to think that an enzyme had a static active site. That's how we thought of it. It was like a lock and a key. Only one key can fit into any given lock. And now we know that an enzyme actually changes in conformation once the substrate binds, and that's that induced fit, okay? Some enzymes need cofactors or coenzymes. So a cofactor and a coenzyme, these are molecules that help an enzyme do its job. I think of cofactors and coenzymes kind of like a tutor for a teacher. If the teacher is an enzyme and the student is the substrate, a tutor, the cofactor, would help the enzyme and substrate work together. The difference between a cofactor and a coenzyme is cofactors are inorganic materials, oftentimes metals, metals. I think I told you that I'm not the best speller. And coenzymes are organic materials, so often they are vitamins, okay? So this is a catabolic and an exergonic reaction that is induced by this enzyme. This could have also been an anabolic had the products here, if this was the start and it was going in this direction. Okay, then it would have been an anabolic and an endergonic reaction. So enzymes can have inhibitors. An inhibitor is something that's going to turn an enzyme off. So inhibitors can be competitive. Competitive inhibitors are substances that bind to the active site and cause the enzyme to no longer be able to bind. And so this is an example of competitive inhibition, where we have the active site bound by this molecule here, and then the substrate can't work. Over here, we have non-competitive inhibition. Non-competitive inhibition also is known as allosteric inhibition. In this case, there's another region on the enzyme that we haven't talked about. It's called an allosteric site. And so you can see it right here. The allosteric region is where another molecule can bind. And when it binds, it changes the shape of the active site. So over here, you see that active site where this substrate normally binds. And over here, the active site has changed because now we have this non-competitive inhibitor binding. And so now this enzyme is no longer functional. In both cases, the enzyme is not going to function properly. So why does this happen? This can happen for different reasons. So one reason would be to inhibit the enzyme from functioning because your cell doesn't need whatever product would be there. So again, here you have an enzyme. Here you have the active site and the allosteric region. In this case, we have allosteric inhibition occurring, and allosteric inhibition, when it occurs, it's causing this enzyme to no longer function. So this often happens in metabolic pathways to inhibit the production of some end product. So an example would be if you have a lot of some amino acid. So you have amino acid, amino acid, amino acid, amino acid, right? And we don't need any more of that amino acid broken down, or we don't need any more of that amino acid built up. We can inhibit this pathway, which is going to not build or break down, whatever. In this case, it looks like it's just converting, right? And we do that by taking some of the end product and using it as an inhibitor. So we bind it to the allosteric region, and now the active site has changed shape, and we're not going to produce any more of that enzyme until we need that enzyme again. So the other type, competitive inhibition, is often seen in poisons. And so we use competitive inhibition when we are trying to stop pathogens. We can poison the pathogen by giving a certain chemical that blocks enzymatic pathways. That's really what happens. Examples would be, I cannot think of the example. So I can't give you the example right off the top of my head, but we have certain drugs that are used in competitive inhibition, and they stop pathogens from producing specific molecules that are needed for their metabolic pathways. All right, I'm going to stop here, and we'll pick up in aerobic respiration in the next video. Bye.